So it says, how much will there be in the account after 3 years if the interest is compounded annually, quarterly, or monthly? Are there any guesses before we start this in terms of like greater or less? So like if it compounds annually versus quarterly, do you think there's going to be more money if it compounds quarterly or annually? Compounding means they apply the interest rate partway through the year to give you interest on that money. As opposed to annually, they would wait until the end of that first full year to compound it, to calculate it, and then give you that interest. Whereas quarterly means they're taking the annual interest rate and they're breaking it down throughout the year, and they're giving you interest in certain increments throughout the year, in certain intervals throughout the year. So this means a quarterly compounding, listen in the back, please, thank you. Eyes up here, guys. Quarterly compounding means that you will be given interest 4 times in that year. Annually means you'd only be given interest at the end of the year. Monthly means you'd be given interest every month. But it's still applying that 4% annual interest to all of these. So do you think you would earn more from quarterly or annual? What's that? I mean, logically, you might think so, but it's actually not. And we saw that a little bit yesterday. So let's see what happens here. So the compound interest formula is here. So what we're going to do is drop the values into that formula that we need to, and then work through it and see what happens. So our value of P, I'm going to go ahead and complete what the table looks like over here. So let's fill in the lines on our table. All right, so the compound interest formula is the amount that we are going to get, A, is equal to the initial investment of $5,000. And that is going to be multiplied by 1 plus R is the annual interest rate, which is 4%, as a decimal is 0.04, over the number of times that the interest compounds every year, the number of times they calculate interest to give to you, which would be 1. And then that gets raised to the number of compounding periods per year and the number of years T. So it compounds once per year, and we're talking about 3 years. So that'd be 1 times 3, which is 3. That's our first equation that we're going to type in. So on your graph calculator, we're going to be able to do this pretty quickly and efficiently because we'll just use the copy and paste feature as opposed to writing this equation over and over and over. So start with 5,000, open up a set of parentheses, type 1, hit plus, go to the math menu, which is over on the left underneath alpha, hit math, scroll over to the fraction column, choose the first option, n over d, type in 0.04 over 1, which I guess is just 0.04. Scroll over to the right, close the parenthesis, hit your exponent button, type in 3. That is the value of your account. That's how much money you will have in your account after 1 year if it only compounds once in that year, which should be more than $5,000. What is it? $5,624.32. Good. So that's what we're going to write in here. $5,624.32. All right, now we're going to alter this to fit quarterly. So A equals 5,000, 1 plus 0.04 over the number of compounding periods per year, which is now 4, because quarterly means 4. It's going to happen over 3 years at 4 times per year. So how many times will it compound over those 4 years? 12. So this number here is actually the number of times it compounds over the entire time frame. So if you're compounding 4 times per year and you're going over 3 years worth, that's going to be 12 total compounding periods. And so what we can do, instead of retyping the entire function, just scroll up a couple of times. It should be, the entire equation should be highlighted in this like light blue. Hit enter, that copies and pastes it. And then you can just scroll back and it's going to go over the 3 there. And I'm just going to change the 3 to a 12 for the exponent. And then on the inside of the parentheses, I'm going to go to the denominator and change the 1 to a 4. So that's all we need to do. So we don't have to retype the whole thing. Hit enter, and that's $5,634.13. So $5,634.13, which means over the 3 years, if it's compounded quarterly, you end up with $10 more over those 3 years than you did if it's just compounding once per year. So if they calculate your interest 4 times per year, you actually get more money that way as opposed to having it calculated once per year. So do you think monthly is going to be even more based on the trend we're seeing? Yeah. So let's write out the formula. So 5,000, 1 plus 0.04. This time it's over 12. What's our exponent this time? 36. So it's going to have 36 periods of compounding interest. So we'll scroll up, copy and paste, scroll back. 36. Denominator is no longer 4. It is now 12. And that's $5,636.36. So 56, 36, 36.
How do you figure out the exponent rate?
So the exponent is the number of times it's compounding per year. So monthly would be 12 times the number of years, which is 3. Yeah. So if we go to if you just go back to the formula here, N is the number of compounding periods per year. And then right here, T is number of years. Yeah. All right. So the answer right here, you can see is the number of compounding periods increases, the amount in the account also increases. So that is what happens. Basically, if you have an account where they compound the interest daily, that's great. You're going to earn a little bit more. If you have a loan that has an interest rate and they're compounding the interest daily, that's not good because that means you're going to be paying more in interest as opposed to earning more in interest. All right, let's talk about this next one. What is the annual growth rate for each possible account? It says using the properties of exponents, you can transform the compound interest formula to find the annual growth rate over a single year. So the first one, annually, let's go ahead and I'm going to get the table drawn back in here. We have A equals 5,000, so our initial investment amount. And then we've got 1 plus 0.04 over 1 to the exponent of 1 to the t power. T is going to be our number of years. So we're talking about, yeah, basically what is, well, we'll talk about this in a second based on what we did on the previous page. So if you remember from yesterday, when we were calculating annual growth rate yesterday, we used a little bit of exponent rules. And so that's what it's saying here, using properties of exponents. And if we head back to that just real quick, we basically said, all right, get the base value in the parentheses, and then apply the fraction from the outside to the inside in terms of the exponent, and then just figure out this number once that fractional exponent has been applied to it. Now, there's not much to do with this particular example. I should have moved that over a little bit further, but there's not much to do with this example because if there's a 1 by the t there, 1 over 1 is just 1, so we don't have to worry about that in any way whatsoever. So it's only compounding once per year, which means if we divide 0.04 by 1, we get, let's just talk about what's in the parentheses here. And gosh, I really kind of messed this up with the amount of space I provided myself. But this is going to equal 5,000 times 1.04 to the power of t. So not applying the power of t means we're not like saying how many years down the road it is. Without the value of t, we're trying to figure out how much is just happening in a single year. So if this doesn't have a number with it for a number of years, we don't know how many years it's happening. We only know the growth rate for a year. And so if it's compounding once per year, the number, whatever's left over in the parentheses here, is our growth rate. And our growth rate is 4%. Because the growth rate is always going to be this number minus 1, which is 0.04. So I should have drawn the line here. The growth rate is 4%.
For
1.04 minus 1. Yeah, so whatever the number in the parentheses is, take away 1 from it, and then whatever's left over is the growth rate, the annual growth rate. So let's try the next one for quarterly. So A is equal to 5,000. Today is the 7th, and it's currently 12:56. All right, we're going to have 1 plus 0.04 over 4, because it's compounding 4 times a year. And then outside the parentheses, we took the number of years, and we multiply it by compounding periods per year. So that's going to be 4t. So the only thing that's different about this versus figuring out the amount in the account is we're not doing number of years because we just want to know the annual growth rate. So we're leaving out the number for years. So the next thing we have to do is we're going to go ahead and divide. Actually, it's not even really division. It's more applying that exponent to, well, I'll show you here in a second. So 0.04 divided by 4 is 0.01. So this is going to equal, I'll just put room down here, 5,000 times 1.01. And then we're basically just taking this 4 out here, and we're applying it inside the parentheses here, 4. The only difference is we don't need a fraction this time because we've already applied all the values we need. So if you take 1.01 and you raise that to the power of 4, what is 1.01 to the power of 4? 1.0406, right? Yeah. So in the parentheses, we get, so we're going to get 5,000 times 1.0406, and then t is on the outside. Which means our annual growth rate is 4.06%. So the interest rate is slightly higher. The annual interest rate, or the annual growth rate, sorry, the interest rate is still 4. If it compounds once per year, the interest rate is the same as the growth rate. If it compounds more than once per year, the growth rate is actually a little bit higher than the interest rate. Which one are we looking at? Are you looking at this number or this number? 4.06. So if you take this and you take this number and subtract 1, you get 0.0406. Converting that to a percentage value is here. Yeah. So basically, drop the 1 and move the decimal 2 spaces to the right. Then you get 4.06 for that. All right, so for monthly, same process, but we're going to put 0.04 over 12, and on the outside, we'll have 12t. So this is going to be, I'm not going to write 8 this time. I'm just going to write 5,000 equals 1 plus 0.04 over 12, and then 12t on the outside. Let's see, 0.04 divided by 12. 0.04 divided by 12 is 0.003 repeating. So I'm just going to write 0.0033. I'll just do 2 3s. There's no real rhyme or reason for that, but more numbers is always a little more accurate. So 5,000 equals parentheses 1.0033. And then we're going to take our exponent and just bring it inside the parentheses and leave the t on the outside. So we're going to have 1.0033 to the power of 12. So 1.0033 to the power of 12. Oops. 1.0033 to the power of 12 is 1.0403. That's a little weird. There you go. What's that? Well, there's 2 zeros before the 3s. Hang on just a second, because it should be higher than that. 1.003 to 12.
Put 5 3 to be 1.0437.
What's that?
Put the more things to put it higher.
Right, and I'm actually looking here at the textbook, and it's a little bit weird because it's only showing 0.003. It's saying this. It's saying, all right, 1.003 like that. And then it's just taking that to the power of 12. And it's saying that it's 1.0407, which is clearly not what that shows. So yeah, the more threes you use, is a better way to do that. So hang on just a second. Let's, instead of translating that to a decimal, let's just go ahead and say 5,000 equals 1 plus, I'm going to do the bracket here, 0.04 over 12 to the 12th power, and then to the t like that. So I'm just going to rewrite it like that, because that way we'll get a more exact value. So if we bring the 12 inside, still keep it outside those parentheses, but bring it inside from where the t was. That way we don't have to worry about estimating a decimal. We can just do this all at the same time. That'll give us a more exact value. So I'm going to do double parentheses 1 plus, and then go back to my fraction, 0.04 over 12. Close the first one. Oops. Delete that. Close the first one. Raise that to the power of 12. Close the second one. There it is. All right, that's the number we need. So a bit of advice here. If you end up with repeating decimals or things like that, go ahead and just write it like this when you're calculating the annual growth rate, just because the more numbers you cut off from your estimate, the further off your estimate is going to be. And so this is going to give us a much more exact value. So that ends up being 5,000 times 1.0407, which is exactly what we want with an exponent of t. So if you subtract 1 from this number and you convert it to a decimal, not a decimal, convert it to a percentage value, that's 4.07. So it's another 1/10th of a percentage point that you get by compounding monthly versus quarterly. Every little bit helps. So in terms of compounding interest, that's how we can figure out our compounding interest based on an annual interest rate. And based on the annual interest rate and how many times you are compounding, you can then convert that to an annual growth rate. Because when you compound things more frequently, your growth increases because you are earning interest upon interest more frequently throughout the year as opposed to just once. This is earning interest once a year. This is earning interest on interest 4 times a year. This is earning interest on interest 12 times a year. And so it just gets a little bit more every single time you compound it. Yeah, question.
Do you only move decimal one?
Twice.
Huh?
Twice. So if the decimal is here, once, twice, puts the decimal in between the 4 and the 0, which is right there. And then same thing here. Once, twice goes in between the 4 and the 0 again. Yeah. It's the same as multiplying by 100, but you can just move the decimal 2 spaces to the right. All right, let's keep going. Any questions before we continue? This right here is exactly what we did right here yesterday. Same thing. Figuring out growth rate from an interest rate. All right. Let's try another example of this here. Try this one on your own. We'll give this one a try. $3,000 is invested in an account that earns 3% annual interest, compounded monthly. What is the value account after 10 years and after 100 years? And then this question here, effective annual interest. That's the growth rate. So just like what we did, I'll just do a little note here. That is growth rate. The only difference between these two equations should be the exponent on the outside of the parentheses of the first two equations, because it's being compounded monthly. Yeah.
I'm trying to find the percentage, it's like,
For part B, you're trying to find the growth rate. That's what the effective annual interest rate is. For the first two, you're just figuring out how much money is in the account. Yeah.
second one, do we have to find it for 10, 100? Yeah.
No, because there's no difference. It has to do with how many times it's compounded per year. It doesn't have to do with the duration of the loan, which is why on the last example, we didn't use T when we were calculating that value. So those are the two answers for A. So over 10 years, after 10 years, you would end up with $4,048.06. Any questions about this first one for 10 years? Okay. After 100 years, it's the same until you get to the exponent, but this time it's been compounded 1,200 times because that's how many months there are in 100 years. And that ends up being $60,031.45. All right. Now, for part B, we're going to say 3,000 times 1 plus 0.03 over 12 to the 12th. And if we take 0.03 and we divide it by 12, that's actually a pretty nice decimal. So I'm just going to leave this as, I'm going to write this as a decimal because 0.03 divided by 12 is a nice decimal. So that's going to equal 3,000 times 1.0025. Bring the 12 inside the parentheses. So 1.0025 to the 12th power gives us an effective annual interest rate of, so let's see, EFF ANN INT rate of what? 3.04%. Yeah, good. There we go. Most of the calculations are done by the calculator. It's just up to you to remember the process. So definitely have these processes in your notes because that'll be the thing to pay attention to. All right. Now, the next thing we get to talk about is something, I think the next thing is really cool. By the way, I love financial math. It's one of my favorite things. My master's degree is in business and my concentration was in finance. And so this kind of stuff is great. I love spreadsheets, like legitimately, they're great. So Microsoft Excel, Google Sheets, all that stuff. So questions before we move on. Yeah. Anybody ever watch Parks and Rec? Yeah. You know Ben from that show? He's like a math, like a numbers nerd, like same. I relate to him. All right. So understanding continuous compound interest. So here we go. Consider an investment of $1 in an account that pays a 100% annual interest rate for 1 year. So if you have $1 in an account and the interest rate is 100%, how much money are you going to have in the account after 1 year? 100% means 100% of the original. So you're going to earn $1 in interest, right? If you have $1 and you have 100% interest rate and it compounds once, you will earn $1. So now your account has $2, right? If you have something and you get 100% of that thing, the amount that you had doubles. Okay, so what we're going to do here is we are going to end up writing in everything that we need to. And we're going to see what happens to our value as we keep working with this. So it says consider an investment. Okay, the equation A equals 1 plus 1 over n to the n to the first n times 1 power is equal to the same thing, but without the times 1, because multiplying by 1 doesn't change anything. This gives the amount in the account for 1 year for the number of compounding periods n. Find the value of the account for the number of periods given the table. So here we go. Get this table kind of filled in a little bit more. So for the first year, we're going to get A equals one plus a 100% annual interest rate. Number of periods n would be 1 this time, so the denominator is 1, and the exponent is also 1 because it's compounding once in that first year. So what's our answer here? 2. You started with $1. You gained the same amount that you had. So you gained $1 from your initial $1. Now you have $2. All right, next. Let's say 1 plus, this time we are compounding 10 times. So it'll be an interest rate of 100%, 10 times a year. So we're still talking about a single year. But now, how much money do we have? Yeah, $2.59. Now, we're going to include some more decimals here because that's going to be useful here. And I made a mistake again. I should not have drawn my line straight down there. That was a mistake. Okay, I'll write smaller. 2.59. We're going to get as many values as we can. 2.59. What is that? 37426. So 2.59. 37426. 4246. There's another 4. It's actually going to be important to write out as many decimals as we can because you're going to notice something that happens as these numbers like increase and increase. You're going to see something change because you might think that this value is just going to shoot up really quickly, but you realize pretty quickly that it doesn't actually do that. So the next one, I'm going to write smaller here. 1 plus 1 over 100 to 100. So that means that if you get 100% annual interest rate, but you compound it 100 times in a year, that's like once every 3.5-ish days. That number ends up being, what do we get that time? 2 point what? Yes, 2.708. 7048. 13829. 13829. Okay. 3 more to go here. I'm just going to go ahead and start writing in the numbers because we know what we're doing now in terms of plugging in values for n. The next one is 2.71 692 3932. So the first time it went up by a factor of 10, you got an additional 59 cents. The second time it went up by 10, you only got like an additional 11 cents. The third time it went up by a factor of 10, you only get an additional 1 cent. The fourth time it goes up by a factor of 10, it's even less than that. So we get 2.7181 45927. It's still going up, but now it's going up very slowly. And if it's 100,000, 2.71 826 8237. Okay. So it ends up going, it continues to increase, but now it's increasing very, very slowly. Everybody see how that's going? So if we kept going, it would continue to increase. But do you think this is going to increase to an infinitely large number? I mean, we've been talking about exponents, right? The first one was talking about exponential growth versus exponential decay. This one seems to be going up like this, and now it's kind of starting to do this. So it looks to me like it's leveling off, right? It shoots up a little bit at the beginning, but it's really starting to level off. And it is leveling off. What's that? It never stops going up, but it never goes beyond a certain number. So there is an asymptote here. Okay, there is a horizontal asymptote here. And that horizontal asymptote, here we go, you ready? Notice that as n continues to increase, the value of the count remains very close to 2.718. This special number is called the natural base. I'm going to highlight that. The natural base. By the way, a base number is simply a number with an exponent. So the number down here versus the exponent, this is your base value, this is your index. So base index. Here, this is called the natural base. The natural base is defined, by the way, first of all, we use the number that we call this is e, lowercase e. You just learned a new number. Lowercase e. This is defined as the value in this particular expression as n approaches infinity. So if you went to infinity on the x-axis, you would get closer and closer and closer to a particular value. And the reason why we write e instead of the decimal value is because e is irrational. What does irrational mean as a number? Goes on forever and never repeats, which means there is no end to this decimal and there's no repeating pattern in that decimal, which means the best way to write that number is by substituting in for something else like e. Or we have another one that's really famous, pi. Pi is by far the most famous irrational number. You're used to using the symbol pi in math problems. You're going to get used to using e as well. So this is just a number that as you take this formula and you approach positive infinity, it's going to get closer and closer and closer to the value of e, which is an irrational number. So I can't tell you what that value is, but it is approximately 2.718-ish. So the number e is the base in the continuously compounded interest formula. So this one here, the continuously compounded interest formula, is right here. So instead of having a bunch of stuff in parentheses with exponents, the stuff in the parentheses with a value of n has turned into e. We're just replacing that. And then we do need to include the annual interest rate, and that appears now with the exponent multiplied by the number of years. So, question for you. If you continued this table for n equals 1,000,000, what would happen to the value in the account? Would it increase or decrease? It would increase, yeah. We just talked about that. If it keeps going up, the value is going to keep going up. It's not going to be, honestly, it's not going to be much more than that. And if we're talking about dollars and cents, you would not earn an additional penny. It would not be worth 1 more cent, but it would be a bigger number than this. So let's go ahead and flip this over and let's use it. So find continuously compounded interest. So Regina invests $12,600 in an account that is compounded continuously. What is the value of the account after 12 years? Round your answer to the nearest dollar. So this time, we're not going to round to the nearest cent. We're going to the nearest dollar. So here we go. Our formula right there. A is equal to P base E exponent RT. So A equals P, principal amount, the initial amount. This is the natural base taken to the exponent of the rate multiplied by the amount of time in years. So the amount here, A, is going to equal the initial investment, 12,600 times E to the rate, which is, what is the rate? 3.2%. There it is. The rate R equals 0.032. Yeah, it was hiding over in the image. R equals 0.032, and it told us it was 12 years, so this is going to be to the 0.032 times 12 power. That'll tell us how much money is in the account. That means you need to find E on your calculator. Oh, man. Anybody see it? Yeah, it's right here. Right underneath where it says log, it's the blue. So we're going to type in 12,600, then you have to type the blue button second, and then hit that E to the X power, and then you can type in your exponent of 0.0 or 0.032 times 12 to the nearest dollar. I got 18,499. I got a different number. Which E did you use? What's that? Oh, you didn't do the 600? Oh, you did 12,000. Yeah, 12,600. So the amount in the account to the nearest dollar would be $18,499. All right. Any questions about that? So this is just kind of plug and play at this point. Throw your numbers in, type it into the calculator, get your answer. All right. Answer A and B on number 4 down here below. We do both of those on your own. Just make sure you convert the percentage into a decimal and you're good. The number of years is doubling, right? Between these two parts, 15 and 30. Do you think there's going to be a doubling in the amount that's in there, or do you think it'll be more than double or less than double? More than double. Probably more than double. It should be. All right.
I think.
So what do we have for the amount of money in the account after 15 years?
204,000.
Yeah, $885. And it doesn't say to round to the nearest dollar, so I'm going to round to the nearest cent. 32 cents, right? So it'd be $254,885.32. That's what I got for that one. So I'm going to guess that there's more than $309,000 after 30 years. 309,000 is roughly double that. But it should be more than double because it's compounding. So that means we should end up with quite a bit more than that. So if I change 15 to 30, that's the only thing that needs to change, 15 to 30. It ends up being a lot more than double, right? What is it? And 23 cents, yeah. $519,732.23. So if you leave it in for twice as long as the original, you end up with way more than twice the amount of money. That's really good. This right here is why it's good to start investing younger. The earlier you invest, the more time your money has to grow in terms of compounding interest upon compounding interest. Doubling the amount of years, in general, more than doubles the amount of your investments. So I can't promise that, obviously, but usually historically, that's how it's worked. So which yields the greatest return on the investment? Quarterly, hourly, or continuously? Continuously, yeah. What does that even mean, though? Let's think about that for a second. That's more than every hour. That's compounding more than every second. Continuously is not a time period, is it? Like to no end. Yeah, like that's a weird concept, I think. Because if you compound hourly, that's 24 times a day. That's a lot of times compounding. But if you compound every second, that's 60 times, or that's 3,600 times that if it's versus compounding hourly. And this is even more than that. This is continuous. So there's no limit to continuous. It's weird to think about. All right, turn the page. Just keep going. We got some more time. Got 12 more minutes. Let's keep going on this. It says, Tia, here we go. Use 2 points to find an exponential model. So we're switching gears a little bit on this next example. Tia knew that the number of instant messages she sent was growing exponentially. All right. She generated a record as soon as Rin gets back. Yeah. She generated a record of the number of instant messages she sent since 2018, each year since 2018. What is an exponential model that describes the data? So we have some information here, and we're going to write an exponential model in our basic exponential model form, a times b to the power of that. So again, switching gears a little bit. In 2022, she sent 6,000 messages. In 2023, she sent 6,600 messages. So what we have to do here, use the data to find the values of the constants A and B. A and B are constant values here. A is a coefficient. Listen up, guys. A is a coefficient. B is a base value. So when data points have consecutive integer x values, the growth factor B is the ratio of their y values. Okay, I'm going to say that again so everybody can hear. You ready? When data points have consecutive integer x values, so they have to be positive or negative whole numbers, they have to be x values, and they have to be 1 apart. So we're talking about number of years from 2022 to 2023. Those are both positive whole numbers, and they are 1 apart from each other. If that is the case, which this is, the growth rate, or growth factor rather, not the growth rate, but the growth factor, B, is the ratio of their y values. So, what do you think that's going to look like? Are 2022 and 2023 integers that are only one away from each other? Yes. So if we take the ratio of the y values, that is going to be, so b, here we go, b equals the ratio, oops, the ratio of the y values. B is equal to y2 over y1, so long as the x values are one away from each other. And because we're talking about growth, the larger number needs to be on the numerator. Everybody good with that? They're one away from each other on the x-axis. Because it's growth, the larger y values on the numerator, smaller y values on the denominator. So what we're going to do is we're going to take 6,600 and put it over 6,000. That's the ratio right there. Now a ratio is written as a fraction. So what does 6,600 over 6,000 reduce to as a fraction? 11/10, yeah, or 1.1. I'm going to simplify it first, and then we can write it as 1.1. So the growth factor, B, is 1.1. So now we're going to use the value of B and one of the data points to find the initial value A. Because right now, we need to figure out two numbers to write this equation. We have one of them. We still need to figure out A. But if we use our value of B, which is 1.1, and we use an XY pair, like 22, not 2022, 6,000, that would not be the value of X. The value of X would not be 2022 because X is years since 2018. So we're gonna have to adjust that a little bit, but the Y value would be 6,000. Let's go ahead and let's use this one here because that's the one that's in the book. So it also tells us, let's see, does it say anything about Y? Interesting, because they are using a different value here, so I'm a little bit curious. Instant message. Oh, there we go. That's what we need to say. So Y is equal to the number of instant messages in hundreds. So we do have to change both of our values for X and Y because X is equal to the number of years since 2018. So here we go. I'm going to say X is equal to what? If we're talking about the 2023, how many years is that since 2018? 5. Okay, so X equals 5. Y is equal to the number of instant messages sent in hundreds. How many hundreds are there in 6,600? 66. All right, so Y equals 66, X equals 5, B equals 1.1. We have to solve for A. All right, let's do it. So 66 equals not 1.1, A, because we need to find A, times 1.1 to the 5th power. We do not have to multiply out 1.1 to the 5th power to do this. In fact, I wouldn't do that. What I would do is I just say, all right, to get A by itself, I need to divide both sides by 1.1 to the power of 5. Those would cancel on the right. And so whatever 66 divided by 1.1 to the power of 5 equals is what A is going to be. So I would just type it into my calculator like that. 66 divided by, or 66 over 1.1 to the 5th power. Which is 40.98. So A is about 40.98. And so if we were to write a function using A and B, because X and Y could be any X and Y, we only use these X and Ys to solve for A. If we're writing a function substituting in for A and B, we're going to get Y equals 40.98 times 1.1 to the power of X. That would be our exponential function. for that particular scenario. All right, let's try the next one and let's see if we can do this one nice and quick. So, number 5, any questions here before we move on? I got the process down. There's a lot of different processes in this lesson. So definitely keep referring back to these when you're working through your assignment, which we'll get tomorrow. We're not going to finish these notes today. We got a little bit more to do. Once we finish the notes tomorrow, though, you'll have the rest of the class just as work time. So, all right, here we go. Number 5. A Kansas realtor reported that the value of an acre of farmland over a period of several years since 2015. The land was worth $2,010 in 2017 and $2,060 in 2018. Use the data to determine an exponential model that describes the value of the land per acre. First of all, are we dealing with growth or decay? Growth, yeah. As the years go by, the value is increasing. So definitely growth. Do we have two x values that are both integers and only one away from each other in this scenario? Yes, 2017 and 2018. Which means that we can take the ratio of those values and say that B is equal to the larger value, 2060, divided by the smaller value, 2010. Which, as a fraction, we're going to write this as a fraction, is going to be 206 over 201. Because the decimal value for that is not nice. 1.02487562, not a great decimal. So that'll be our value B. Okay. Now, let's start writing an equation. So we need y equals a times b to the power of x. We're not converting anything with the values of y. So let's just use the 2017 value here. So that'll be y equals 2010. Which means x is equal to what? The value of $2,010 happened in 2017, but what does x equal in this scenario? 2, yeah, because x is the years since 2015. So x equals 2, and b is equal to 206 over 201. So we're just going to plug those in for x, y, and b. So here we go. Y is equal to 2010. Times a, and then we're going to get 206 over 210. I'm going to put that in parentheses, all to the power of 2. I don't really care what that number is as a decimal, so I'm just going to divide this by both sides, or on both sides. 206 over 201 squared, divide by 206 over 201 squared, and that will give us our value of a. So go ahead and put your stuff away. We'll finish this all up tomorrow. You got your assignment yesterday, right? Okay. Before you come back tomorrow, please finish this example. There's only a little bit left. That'll be what I want you to finish up so you can double check that when we start class tomorrow. We'll spend about, I don't know, 10, 15, or 20 minutes going over this last one. And then from there, you'll have the remainder of class just to work. So that's all I got for you today.